Welcome to the deep dive. Today, we're really getting into the weeds on why the best reasoning AI models out there. You know, the big ones like OpenAI's O1 or maybe DeepSeek's R1, why they use this specific two-stage training approach.
Right. We're looking at this paper, How Reinforcement Learning After Next Token Prediction Facilitates Learning, by Syllabus and colleagues.
Exactly, and it digs into that standard recipe. First, you pre-train a huge model predicting the next word, next token NTP.
On basically the whole internet.
And then you fine-tune it using reinforcement learning RL to get it really good at specific hard tasks.
Yeah, rewarding it for correct answers on those tricky problems.
Okay, so for the crucial first-minute summary, the big insight from the paper is this. They argue, and they show theoretically, that if the complex reasoning steps the chain of thought, Kati are already somewhere in that pre-training data, even if they're super rare.
Like finding a needle in a giant haystack.
Exactly. Then the RL phase acts like a super efficient data miner. It doesn't really teach new stuff, but it massively boosts the model's tendency, its policy, to actually use those rare, long, correct reasoning chains.
It forces the model to generate them.
Right. Leading to this exponential jump in producing long, accurate Kati answers and ultimately perfect generalization on the task, which NTP alone just couldn't achieve.
So the bottom line is RL solves a kind of utilization problem. The knowledge is there after pre-training, but the model doesn't use it effectively until RL forces it to. It shifts the odds dramatically and surprisingly fast.
Okay, fascinating. Let's unpack that. We need to understand the standard process first, and then why does NTP fail in this specific way that RL needs to fix?
Okay, so the standard paradigm has two key ingredients. First, pre-training. You take a massive autoregressive transformer, GPT, Llama, Mistral, whatever, and you train it on just petabytes of text data using that next token prediction objective. Just predict the next word over and over.
Right, which makes it great at language, fluency, knowing facts. Basically a huge knowledge base. And sometimes supervised fine-tuning, SFT, gets lumped in here too, right? Training on curated examples.
Yeah, exactly. SFT is often part of this broader pre-training or initial tuning phase. But the core observation, the thing this paper tackles, is that for really complex reasoning math problems, logic puzzles, the big performance jump often happens after that, during the reinforcement learning stage.
That RL stage. It's often described as kind of a guess and check loop, isn't it?
Sort of, yeah. The model generates potential answers or guesses. A reward function checks if they're right or wrong, or maybe how good they are.
And then the model's policy, its strategy for generating answers, gets updated to maximize that reward signal.
Precisely. And the really noticeable thing, especially for us technical folks watching these models train, is when they get better at reasoning, the answers get longer.
The chain of thought emerges, the model starts showing its work.
Exactly. It starts spitting out these intermediate steps, the reasoning process, which maybe wasn't happening much before or wasn't reliable.
So the paper's central mission is to explain why. Why does this two-step dance work so well? Assuming, crucially, that the KTPAPs were already learned, just hidden or suppressed after pre-training.
Right. And to do that, theoretically, they needed a problem simple enough to analyze mathematically, but complex enough to require that kind of step-by-step reasoning.
What did they pick?
They landed on a classic, predicting the parity of d bits.
Okay, are there an even or odd number of ones in a sequence of bits?
Exactly. And the neat thing is, this is known to be hard for shallow networks if you don't show the intermediate steps. You kind of have to compute partial parities along the way. It forces a sequential process, a nice proxy for chain of thought.
Clever. So how did they set up the data for this?
They created this data distribution, let's call it DCOT. It's a mixture, and the PCOT is the key parameter. It's the probability of seeing the good data. So most of the data, like $1 COT fraction, consists of short sequences. Just the input bits, and boom, the final parity answer. No steps shown.
Right.
But a tiny fraction consists of long sequences. These have the input bits, all the intermediate calculations, the partial parities, and then the final answer.
And they focus on the case where PCOTs is really small, right? Like maybe 1 in a million examples shows the full reasoning.
Exactly, reflecting the real-world scenario where detailed Kati is rare in web-scale data.
Okay, so now, Theorem 1. This is where the failure of just NTP comes in, right? What happens when you train only with next token prediction on this mixed data?
Right. So the model actually does learn correctly in one sense. It achieves what they call length calibration. It correctly estimates the conditional probabilities. It knows, based on the data, the likelihood of seeing a long sequence versus a short one. It learns the PAC ratio.
So it knows the structure of the data. That sounds good.
It sounds good, but here's the catch. When it comes time to actually generate an answer using greedy decoding, just picking the most probable next token at each step,
Yeah.
if that proportion of long Kati sequences, IOCOT, is too small specifically, they show if Caracal is less than 3 in their setup, the model consistently fails.
Fails how? Does it get the answer wrong?
It generates a short sequence. It basically just gives the input and maybe tries to guess the answer immediately, or even just stops EOS. It never generates the long step-by-step Kati sequence needed to actually solve the parity problem correctly.
Whoa. So even though it saw the correct long sequences and it learned their probabilities, it refuses to generate them if they're too rare.
Refuses is maybe anthropomorphic, but yeah. The optimization process itself, maximizing the probability of the next token given the overwhelming frequency of short sequences, makes it statistically prefer the short path, even if that path leads to a wrong answer.
Okay, wait. Why 13-year-old dollars? That number sounds weirdly specific. Is it fundamental or just for the parity problem?
Good question. It comes out of the math for the specific linear model they analyzed for the parity task. The core idea is broader, though. When you have a long sequence of steps, even if each step is reasonably likely, the cumulative probability of successfully navigating all those steps can become quite small.
Right, like P step 1, P step 1, and so on.
Exactly. And if the probability of just outputting a short sequence directly, even if it's wrong, is higher than that cumulative probability of the entire long correct path,
Then greedy decoding picks the short path, even if the long path is the only way to be right.
Precisely. If PAYCOT is below that threshold, the immediate probability bump from starting a short sequence outweighs the uncertain multi-step prospect of the long one. It's a failure mode inherent to NTP on this kind of mixed data with rare long solutions.
Wow, okay. That really nails the problem. The knowledge, the capacity to solve it via Kati might be baked into the weights from those rare examples. But the NTP objective function itself prevents the model from accessing or executing that strategy during generation. It learned the right thing, but makes the wrong choice.
You got it. And that is why RL becomes the hero here. It changes the game entirely. They looked at a few RL algorithms, standard ones like reinforce, GRPO, and also, importantly, an algorithm called STAR, which stands for self-taught reasoner.
STAR. Okay, I've heard of that. But wait, isn't STAR sometimes described as just like generating answers, filtering the good ones, and then fine-tuning on those? That sounds a bit like supervised fine-tuning again. Why call it RL? What's the key difference?
That's a really sharp point. STAR does use an objective that looks like SFT or NTP for the actual weight update step. But the crucial difference is how the data for that update is selected.
Okay.
In STAR, the model generates samples using its current policy. Then you use a reward function like, is the final answer correct? Rewarded with 1 if yes, 0 if no. You filter the generated samples based on this reward.
So only the successful generations get used for the next round of fine-tuning.
Exactly, and you do this iteratively. Generate more filter by reward fine-tune on filtered set repeat. That act of selecting data based on maximizing a reward signal is fundamentally a reinforcement learning process. You're using the reward to dynamically shape the training distribution, focusing only on the model's own successful outputs.
I see. So it's the reward-based filtering and the iterative policy improvement loop that makes it RL, even if the update looks like SFT.
Precisely. It's creating a new, highly biased training set, dillion text filter dollars in each round, based purely on success.
Okay, cool. And this star-like process, or RL more generally, is what leads to the exponential speedup. Theorem 2.
That's the one. Theorem 2 shows that this RL fine-tuning process dramatically shifts the effective data distribution. Remember, the initial low probability of a long sequence. Let's call the probability after 1 lons of RL P-Aller.
Okay.
The paper shows that P-Aller converges to 1, meaning the model only generates long sequences exponentially fast. In the ideal case, the update rule is roughly Pn plus 1 plus frac Tn1 plus Pn.
So it bootstraps itself very quickly.
Very quickly. The number of steps needed to get the model to reliably generate the long Kati responses scales logarithmically with how rare the sequences were initially. It's logarithmic scaling. Okay, let's put on our ML engineer hats. What does that mean practically? If TCOT is like 1 in a billion, super rare, how much compute does this RL approach save compared to just trying to find more Kati examples for SFT?
It'd say it's a ton. Logarithmic scaling is incredibly powerful here. If t-cut is tiny, finding enough good examples just by sampling more data for SFT would require an astronomical, maybe practically impossible number of samples.
Yeah.
You'd need to sift through billions or trillions of examples just to find a few good ones.
Right, the sample complexity would explode.
Exactly. But the log scaling means null, or the number of RL steps stays really small.
Yeah.
Even if t-cut is $1 in $1 billion, the logarithm goes incredibly slowly. You might only need, say, 20 or 30 RL steps to completely flip the model's policy from preferring short wrong to preferring long correct.
The RL process isn't finding the needles by searching the whole haystack directly. It's using the reward signal as a magnet to pull out the successful strategies indirectly and then amplifying them extremely rapidly. It sidesteps that massive sample complexity problem of the original data.
Okay, that really clarifies the data mining accelerator idea. It's not just faster mining, it's using the reward to unlock unusable knowledge with logarithmic efficiency. That's powerful.
Yeah, it's a really neat theoretical result. And the cool part is they then showed this isn't just theory, it holds up empirically on actual complex LLMs.
What models and tasks did they use?
They tested on Llama models specifically. I think it was Llama 3.23b and 3.18b variants. And they used tasks like multi-digit number multiplication and standard math benchmarks.
Okay, multiplication. How did they set that up to test the Kati aspect?
They made it tricky. They encoded the numbers with digits reversed, which forces the model to really track intermediate states like carrying numbers in grade school multiplication. That whole trace is the Kati. And they created datasets mixing examples that showed this full trace, the long sequences, with examples that just had the question and the final answer, the short sequences.
And what did they find when they compared NTP-only training versus NTP plus RL?
They found exactly what the theory predicted. The benefit of adding the RL post-training stage got bigger as the task got harder.
Oh, interesting. How so?
Like when moving from easier $2 times 2 multiplication to harder $5 inside 5 multiplication, the accuracy gap between the RL-tuned model and the NTP-only model widened significantly.
So the longer and more complex the required reasoning chain.
The more crucial that RL mining step becomes to actually unlock and utilize that reasoning ability. It helps most when the Cauchy is longer and thus likely rarer or harder to execute correctly.
Makes sense. What about the standard math benchmarks? GSM-8K, math.
Yeah, they tested on those too. Here they used datasets where the Cauchy was explicitly marked out using special tags like think actual reasoning steps, think answer, final answer, answer.
Okay, so very structured Kati.
Right, and they designed the RL reward function to specifically encourage generating this structure correctly.
How did the reward work there?
It was often stepwise. Maybe you get a small reward, like 5 points, just for correctly placing the answer tag after the thinking part. And then a big reward, like 100 points, if the numerical answer inside the answer tag is actually correct. So it rewards both the structure and the final accuracy. It scaffolds the process.
And did they see the same kind of shift in behavior during RL training?
Absolutely. They have these figures in the paper comparing generations early in RL versus later on for GSM-8K, for instance. It's night and day.
Really?
Yeah. Early on, maybe after just one RL step, the model generates short, garbled stuff, often gets the answer wrong. But you fast forward to, say, step 58, and suddenly the generations are long. They look almost exactly like the ground truth Kati examples, step-by-step reasoning, correct structure, and crucially, much higher accuracy. The shift is dramatic.
So it really learns to think out loud and get the right answer through that RL process.
Precisely.
Yeah.
Which led them to hypothesize about these two learning phases in RL.
Two phases.
Yeah. They suggest the initial really steep improvement you see is mostly this in-distribution learning. That's the rapid logarithmic data mining effect we talked about. Finding and amplifying the Kati knowledge already present from pre-training or SFT.
Okay, activating latent knowledge.
Right. And then after that initial surge, the improvement might slow down. That slower phase could be more like out-of-distribution generalization, where the model is perhaps learning genuinely new variations or extensions of the reasoning pattern.
Interesting distinction. So mining first, then maybe slower, broader learning.
That's the hypothesis, yeah.
Okay, so wrapping this up, the main takeaway from Silvus and colleagues is that they provided this solid theoretical grounding for why RL fine-tuning is so effective for reasoning. It's not magic. It's this efficient mechanism for exponentially boosting the probability of using rare, complex, but correct reasoning sequences that were learned previously but weren't being utilized.
Exactly. It's a reward-driven policy shift that makes the model actually use its deepest knowledge. And this reframes how we should think about that increase in response length we see during RL tuning.
How so?
It's not just some side effect like the model needs more scratch space. The paper argues it's a core part of the learning process itself. The optimization forces the model towards generating those longer explicit reasoning chains because that's what leads to the reward. The length increase is the learning phenomenon, in a way.
That's a really key insight. The length is causal, driven by the optimization.
Yeah.
Okay, final thought then. The paper shows the benefit of RL gets bigger for harder tasks, right? Where the reasoning is more complex.
That's what the multiplication results suggested.
So does this imply that for the really frontier challenges in AI, the super complex problems we want models to solve, maybe the bottleneck isn't just cramming more data into pre-training?
It's an interesting question.
Could it be that success hinges more on how cleverly we design these RL stages? How effectively can we use reward signals to excavate those incredibly rare, deeply embedded reasoning capabilities that might already be latent in our giant pre-trained models? Perhaps the path to superhuman reasoning isn't just scale, but smarter excavation.
That's definitely a provocative thought. It suggests the post-training phase might be even more critical than we currently realize for unlocking the highest levels of capability, something for all of us building these models to think about.
Definitely food for thought. Thanks for digging into this with me today.
My pleasure. It's a fascinating paper.